Okay, thank you very much for the invitation. So I would like to speak about group actions on cluster categories, which are constructed from mutations at frozen vertices. And the plan is as follows. In the first part, I'd like to present the blue versus red game. As you perhaps know, blue and red are the colors of the two major parties in the United States. But believe me, this game has nothing to do with American politics. And then in the second part, I'd like to apply the outcome of this game to construct actions of subgroups of Braid groups on cluster categories as promised in the title. So let's look at the blue versus red game. So we fix an ice quiver. Well, that's just a quiver with a distinguished subquiver denoted by F and drawn in blue. The frozen subquiver. Now, as you know, Fomin-Zelwinski introduced mutation of quivers at non-frozen vertices, but in their definition, they neglected the arrows between frozen vertices. And recently, Matthew Presland refined their rule so as to take into account the frozen arrows, the arrows between frozen vertices. And even more recently, Elin Wu observed that Presland's mutation rule also makes sense for mutations at certain frozen vertices, namely frozen sinks and frozen sources. What is a frozen sink? Well, it's just a sink of the frozen subquiver where we have only outgoing non-frozen arrows and purely for a frozen source. Okay, and so now we can start mutating at frozen vertices, at certain frozen vertices, frozen sinks and frozen sources. So here we have an example. This is an example of the blue versus red game. It consists of two phases. The first phase, which can be called the reform phase, goes as follows. Yes, we choose a sequence of frozen sinks or sources and perform mutations at these. So an arbitrary sequence of frozen sinks or sources, but only frozen ones, yes. And then, thanks to this sequence, we transform our quiver into a new quiver. As you can see in this example, the new quiver is just the opposite quiver of the original one, but in general, it will be more complicated. So this is the first phase of the game with the reform phase. And then we have the counter-reform phase, where we use mutations at non-frozen vertices, red vertices, to undo the effect of the reform phase. So, well, this doesn't always work, but we try our best, and sometimes it does work. Now, in this example, just by mutating at this central vertex, we can reverse the orientation of the quiver. And so in this example, we get back exactly to the original quiver. In general, often we come back not exactly to the original quiver, but the original quiver up to an isomorphism. So let me show you an example of this slightly more general situation. Here it is. Okay, so here we have another ice quiver, and we first perform the reform phase with mutations only at blue vertices, here at 1 and at 6. And now we try to undo the effect of this by mutating at 8, 4, and then at 5 and 7. So let's try 8 and 4. Oh, I'm sorry. And 5 and 7. Okay, yeah, I'm sorry. I didn't prepare this. I made a mistake in preparing this. So, well, if I had properly prepared it, then by performing a cyclic mutation of these vertices, I would have gotten back to the original quiver. Let me show it to you on the notes. Yes, so this is what happens here. We perform mutation at 1 and 6, and then we perform mutation at these 4 vertices. We get to this quiver, but not exactly the original quiver, but the original quiver up to a cyclic permutation of the non-frozen vertices. Okay, and now let me use the outcome of the game to construct a braid group action. So, well, we keep our ice quiver and we keep the outcome of the blue versus red game. And now we look at the braid group associated with the frozen part of the quiver. It has one braid generator for each vertex of the frozen part, and it has one braid relation whenever we have a unique arrow between the two vertices. And now this braid group has a nice categorical lift via spherical twist. This braid group acts on the perfect derived category of the Calabi-Yau completion of the path algebra of the frozen part. Well, that's just an enhanced version of the pre-projective algebra. And the simples form a spherical collection, and that's how this braid group acts. And now we look at the blue part here, and with the blue part, we associate an element of the braid group, just the product of the braid generators associated with the vertices in our blue sequence. And the idea is that this element should act on the cluster category. And for this, in order for this to work, we need additional assumptions. We need to assume that we have a potential which has three key properties. It should be consistent, which means that the relative Ginzburg algebra is concentrated in degree 0. It should be epic, which means that the Ginzburg morphism from the pre-projective algebra to the boundary algebra is a ring epimorphism. And thirdly, it should be preserved under the mutation permutation sequence, which is the outcome of the blue versus red game. Okay, and now with such a mutation permutation sequence, we can associate a canonical auto-equivalence. Yes, every mutation leads to an auto-equivalence, and we compose all these to get this associated auto-equivalence. And the claim of the theorem is that this auto-equivalence only depends on the element of the braid group associated with the blue part of the outcome of the blue versus red game. And this then implies in particular that, well, when we vary the outcomes of the games, well, then these elements of the braid groups will satisfy relations inside the braid group, and the same relations will be satisfied by these auto-equivalences. And in this way, we get an action of a subgroup of the braid group, well, the subgroup generated by these, on the perfect derived category of the Ginzburg algebra, and therefore on the relative cluster category, which is a canonical quotient of the perfect derived category. And then by decategorification, we also get an action on the cluster algebra. More precisely, we get a morphism from this subgroup to the group, to the quasi-cluster modular group of our ice quiver. And well, so this, in principle, this depends on this subtle property of preservation of the potential under the permutation mutation sequence, but we conjecture that this is actually unnecessary. We only need the two first conditions for this to happen, for this purely combinatorial phenomenon to happen. Okay, well, there are classes of examples. The first example is a Grassmannian braiding as introduced by Chris Fraser in 2020. And there is a generalization of this where we have, instead of an action on the Grassmannian, we have actions on positroid varieties inside the Grassmannian. And in this case, it is really a proper subgroup of the braid group which acts. This is recent joint work with Chris Fraser, and we expect many, many more examples. So to conclude, here you have the references in the notes. You can even click on these links. And finally, I'd like to wish you all a very happy, healthy new year from Hefei, where I'm presently based. Thank you very much.